let me just give a little bit of background. I sometimes think of GIA as this three-legged stool. So certainly it's not a research institute in its entirety. It has a research leg, it has an education leg, and we have a laboratory that tests and grades gemstones. So, and most of the research done at GIA is applied, so to solve gemological issues that exist in the industry. So today, first we'll talk about synthetic diamonds and the recent changes, and I would say recent in the last 20 years, but more recently in the last few years. And I'm sure you've probably heard or read much about this, and it's been in the public media quite a bit recently, and how it's going to impact natural diamonds. But I think he'll focus on the identification. So we.
Good afternoon, everyone. So as Tom mentioned, I'm currently a postdoc at the GIA, and I'm working mainly on determining provenance of colored gemstones. Most of this work is done in collaboration with Graham Pearce and his group at the University of Alberta. Right, so yeah, since we're talking about gemstones, I thought it would be nice to show a few pictures to start with. And as you can already see from the dates, gemstones are really very much timeless. They're always in fashion, they're always in style. But what makes gemstones really precious? Why are they valuable? As we mentioned, for diamonds, it's mainly due to their rarity. But there's also other factors. So color is the main one, as you can see in this nice pie chart. The cut also has an influence on the value, the size as well, and the shape. And more recently, the location of where a different colored stone comes from can also affect the value. You can see here in this graph on the side that this source is also, again, correlated with rarity. So this started in the 1950s, but in the 1990s, there was a sudden increase in consumer awareness of both provenance of gemstones and also the mining procedures. And so the gem industry or gem labs were really forced by the trade to offer origin determination, to offer origin opinions on their reports. The main reason for this is, as I mentioned, the prestige of certain mines. So historical locations like Burma or Myanmar nowadays are known for their exceptional colors, and therefore if a stone comes from there, the value can increase. And another reason here is the need for traceability due to fair trade movements and political bans. Yeah, here, this is a nice map from AmericanScientist.com, and you can see for a few different gemstones varieties that we have deposits all around the world, so ruby and sapphire, here in Africa, Madagascar, up here in Asia, we have some in Australia, as well as over here in North America and South America. So to determine the geographical origin, you can imagine, is quite challenging. Gemstones also form in different geological formation environments. Roughly, we can divide them into three types: magmatic, metamorphic, and sedimentary. However, as you can see in these pie charts, they can actually be further subdivided. I'm not going to go into any detail about this here because we don't have the time. But as I want to show, so for example, for ruby, you can have stones from 3, 4, 5 different geological deposit types. They are mainly metamorphic in origin, though. And the same here for sapphire, emerald, and saviorite. As you will see throughout the presentation, it is much easier to distinguish between sources with different geological settings than it is to distinguish gemstones from different geographic regions, but similar geological settings. So, yeah, for what colored stones varieties do we do origin determination? So there's actually a number of stones, but the really big value differences only happen here with these big three, ruby, sapphire, and Columbia. So you can see this Sunrise ruby sold in 2015 for $30 million, and it's a 25.59 carat stone. Similar here, this is a big difference again to the sapphire, which sold for only $5 million in 2014. And this nice Rockefeller emerald from Colombia actually just sold 2 days ago in New York for $5.5 million. Yeah. So these are really the ones that are important. My work was mainly, or is mainly on ruby and sapphire. That's why I'm going to focus on those stones. So we utilize several different techniques to do origin determination. The most traditional one are optical observations. So here gemologists look at inclusion landscapes because some mines produce stones with very diagnostic features that can really only be found at one single location. As these intersecting and twinned rutile needles in ruby here, they are very diagnostic for rubies from Burma. You can also look at growth patterns. One example here is this nice blocky, milky zoning of this blue Kashmir sapphire, as opposed to very dense zoning that is found by the Madagascar counterparts. Unfortunately, these features aren't always present in the gemstones that we look at, so optical observations alone won't give us the geographic origin. So what we then can also use is spectroscopy. So we use Raman mainly to characterize the inclusions because they can give us some indication of where the stone could come from. For example, calcite in a ruby would indicate marble-type ruby. So this could help us. What we also use is UV-vis absorption that can give us a spectral fingerprint. One example here for blue sapphire. So we have a spectrum here in light blue of metamorphic sapphire, and then in dark blue, a magmatic sapphire. And this magmatic sapphire also has an absorption feature here at the iron 2+, iron 3+ intervalence charge transfer. And this is never seen in metamorphic sapphire, regardless of their iron content. So just using UV-vis, we can already narrow down the origin quite significantly. So the perhaps most powerful technique used right now are trace elements, because trace elements fractionate in differing fashions in different geological conditions. So different trace element abundances or ratios can give us a geochemical fingerprint of a certain origin or a certain region. So what techniques that have been used are both non-destructive and quasi-non-destructive. So EDXRF, electron microprobe analysis, that mainly at universities, not so much gem labs. Most often nowadays, gem laboratories have laser ablation ICP-MS systems because they're relatively affordable. They have a high turnover. It's relatively easy to use, and the detection limits are pretty good. And another technique that is also coming is laser-induced breakdown spectroscopy. Yeah, again, as I said, I'm going to focus mainly on corundum. And for corundum, we look at trace elements that are substituting into the corundum lattice for aluminium 3+, because there the abundance is high enough, and there's quite a lot of variety. Unfortunately, this only gives us about 6 elements to work with right now, and it's chrome, iron, titanium, vanadium, gallium, and magnesium. And so if you look at this bivariate magnesium-iron plot, we can see that if we just look at the different geologic origin of the rubies, we get a very good separation just using trace elements. So in red, we have the marble-type rubies, and then blue amphibolite-type rubies, and the basalt type are also distinct. However, if we then plot the same data by mine or by geographic region, we can see that we have quite a bit of overlap, especially here among the marble-type rubies, and also here the amphibolite-type rubies. So some of the work I've been doing is to try to get more quantitative data for additional elements. Those are mainly only in the ruby at ultra trace levels. And that's why we used a very large spot size, as you can see here, 285 micrometers. That would not be possible at a gem lab, but it's still academic research. So we analyzed a number of different locations, and if we plot them in this triangular plot, so this is one of the first trace elements plots that has been published, and it actually shows some good separation. So you have like rubies from Tanzania down here, Myanmar, it's more concentrated up here. So there's quite a bit of overlap still. Same if we look at it more closely here, the amphibolite type stones. So yeah, doing our research, we actually got quantitative data though for up to 30 elements. In some cases, not in all. Most of them have not proven very useful in origin determination. However, as you can see here in this triangular plot, nickel has proven to be quite useful, at least among the localities that are analyzed. You have to realize, unfortunately, there are even more, so that could change the whole picture again. But the data set that I have, if you use nickel with titanium and vanadium, and then you can further subdivide it by gallium and iron, then you get the Madagascar samples out that overlap here with the population of Greenland rubies. And then if you further look at these samples using calcium and magnesium, you can separate them out. So it's always like a several-step process. There's still some overlap here, as you can see, but it is getting better. When we look at the marble-hosted rubies, the overlap is much more severe still, as you can see. Using tin, we actually can extract some of the Vietnam rubies, which are really the culprit here, because they plot over everything, whereas Myanmar and Afghanistan and Tanzania are somewhat separate. So this is an element that we can maybe look at, or at least it can help us a bit more, but we're really not quite there yet. At the moment, Matt Hartman, a PhD student of Grams, is doing some advanced statistics on this data set, which is a bit difficult because it's still not quite enough data. At least he's validated some of my findings and yeah, is looking to improve things. But so far, we're still at the level where trace elements alone cannot tell us the geographic origin, without a doubt. So another technique that has been looked at or explored are isotopes. A lot of work has been done on stable isotopes, oxygen, on corundum especially, but also emerald, spinel, and saviorite. This has been done using laser fluoration mass spectrometry. Unfortunately, not a non-destructive technique, so you need about 1 milligram of ground corundum to get the delta 18O ratio. This has been found, or this is very useful to constrain a geological source. So as you can see here in this nice plot from Giuliani et al. If we have marble-type ruby, it falls in at very high delta 18O values, whereas rubies in metamorphic metasomatic rocks, so here this would be the amphibolite-type rubies. They are quite distinct. However, if we had samples from different localities of this type, that would still overlap. However, this is useful if you have samples from a placer deposits, and quite a lot of gemstone deposits are secondary to determine the geologic source of the stones in that deposit. So what we have been exploring recently are radiogenic isotopes for the use in geographic origin determination. I don't know if you remember this nice graph yesterday, Graham showed it for the boron isotopes in diamond. So we've been using it on ruby to determine the strontium and lead isotopes. Just a refresher, this is a closed cell environment, and we place the stone inside and then can ablate for several hours to accumulate the amount of material that we need. This is also not a non-destructive technique. Here you can see a nice ablation pit on a ruby from Madagascar. So none of the elements that are involved in the rubidium, strontium, uranium, thorium, and lead system actually substitute into the crystal lattice of corundum. However, they are present in submicron to micron sized inclusions in the lattice, and this is what we're bulk sampling with this technique. So here, a quick look at our results. So here we have an 87 strontium over 86 strontium versus 207 lead over 206 lead plot. And as you can see, for amphibolite type rubies, the analyzed samples do fall into discrete fields. So here we have Mozambique, Tanzania, and Madagascar. Samples from Greenland have a very distinct signature, so they're much more radiogenic. This is due to their old age. So we've dated them to about 2.7 billion years, whereas samples from these three localities are between 500 and 16 million years old. So there's much more distinct. However, as you can see, we do have distinct fields for these localities. However, if we look at marble type ruby, as well as some metamorphic blue sapphires that we also looked at, we have significant overlap. So unfortunately, for these types of stones, this technique doesn't seem to be very valid. Right. So yeah, what I haven't specifically mentioned, but it was implied, is the way we do origin determination is that we have an unknown sample and we compare it to a database of known samples. And because of this approach, the completeness and reliability of this stone collection is really essential. This can be quite difficult, which is due in part due to sample availability, especially if you look at more historic sources. It can be quite pricey to get samples, and you also need a representative number of samples. So that can be difficult. In addition, the mining, when it comes to colored stones deposit, is not, as it is in diamond, very large scale and centralized, but instead we have a lot of small scale operations. They can be in very remote locations. Very often the deposits are pretty small, so they're discovered, and then after 2 or 3 years they will be already exhausted. And then there's always a lag. So the trade, of course, wants to keep the new source quiet, and by the time it comes to the gem lab, a bit of time may have passed. And thirdly, there's also quite a bit of heterogeneity within the gemstone deposits. So you have to be careful that you sample all of it if you get a chance to go and actually sample it. So this can be very difficult. GIS actually has a really good field gemology department. So our colleague Wim actually travels quite extensively and collects samples. Of course, we also face analytical challenges. So if you collect data every day, you have to be really on top of the quality of the collected data and also the data processing. You also have to make sure to be consistent. Otherwise, you won't be able to compare your data to the sample base. Another issue or challenge in geographic origin determination is the transparency. So unfortunately, it's not uncommon that a client will submit a stone to 3 different labs and then get 3 different origin opinions back. Gemological laboratories nowadays, they don't have to tell you how they arrive at their opinion. There are no standardized procedures. So this is also quite a challenge. Of course, they also don't like to share the data. Yeah. So as I think I've shown quite well, we don't actually have a unique fingerprint so far. Origin determination still requires a holistic approach. So you have to do a combination of gemological observations, you have to collect scientific data, and you have to have a reliable reference sample database. And even with all of that, origin is still just an opinion, because it is very difficult to especially determine between deposits of different geographic origin, but similar geological origin. So for the future, I think it's very important that we keep refining our existing techniques. Laser ICP-MS has a lot of potential, but we also need to continue exploring for new techniques. It would be great if we could increase transparency of the techniques and procedures used in origin determination. Ideally, we would want standardized origin report requirements. And lastly, the continued exploration of gemstone deposits is also essential, because we need this reliable sample base, but also the more we know about gemstone formation, the easier it will be for us to actually find new ways to distinguish between the different deposits. Okay, and with that, thank you very much. And just like to thank my collaborators as well.